Hello everybody. It is a delight to be back in Moscow and to talk to you today on the frontiers of fundamental physics. The questions that we are asking that define the difference between what we know and what we don't know. That's what I mean by frontiers. We actually know quite a bit about what makes up matter in the universe and the laws of physics. And in the last part of the 20th century, we studied and learned to understand what goes on inside the atoms that we are made out of. We have identified the basic elementary particles, the basic constituents of matter, the electron that moves around the nucleus of atoms, and determines the structure of atoms and molecules. And in the latter part of the 20th century, we probed into the small nucleus at the center of every atom and discovered the quarks that make up the nuclei, the protons and neutrons inside the nucleus. And we have identified the three forces that act within the atom, the force of electricity and magnetism, and the two forces that act within the nucleus. The so-called strong nuclear force that holds quarks together and nucleons together in the nucleus, and the weak nuclear force, which gives rise to radioactivity. Study nothing. I study the properties of the vacuum. You know what the vacuum is, right? If you take this room and remove everybody, all the people, all the chairs, all the lights, all the atoms, all the molecules, you turn off all the electric and magnetic and other fields, you're left with the vacuum. Nothing. That is the picture that most people have of the vacuum. Pretty boring. But in quantum mechanics, that is not the case. And we know now that the world is quantum mechanical. And in quantum mechanics, there can't be anything that is that boring because nothing is ever at rest. For example, if you have a pendulum, like a clock, here's a pendulum. It's moving, right? It has energy moving back and forth. Now, the vacuum is like when you stop the pendulum, so it's motionless. Boring. But if you try to see whether the pendulum is indeed at rest, you have to shine a light on the pendulum. And the quanta of light hit the pendulum and make it move. Up quark and the anti-up quark, or the up quark and the down quark, and so on. Because there are two kinds of charges, a new thing can happen. Oh, and in terms of particles, we say that this force is mediated by a field now with more quanta, because there are more charges. These are called W and Z mesons. And a new thing can happen. An up quark can emit a W meson and turn into a down quark, a neutrino, and positron. The up quark is usually found inside the proton. So when this happens, a proton turns into a neutron, and a positron and a neutrino. That, when the proton is inside, say, for example, gold, means that gold turns into platinum. This is what is called beta decay, radioactivity, and the anti-up quark, or the up quark and the down quark, and so on. Because there are two kinds of charges, a new thing can happen. Oh, and in terms of particles, we say that this force is mediated by a field now with more quanta, because there are more charges. These are called W and Z mesons. And a new thing can happen. An up quark can emit a W meson and turn into a down quark, a neutrino, and positron. The up quark is usually found inside the proton. So when this happens, a proton turns into a neutron, and a positron and a neutrino. That, when the proton is inside, say, for example, gold, means that gold turns into platinum. This is what is called beta decay, radioactivity. But they're not massless. And the reason we understand, we think, we're very sure, that they get a mass, the reason they get a mass, we think, is because of another field that we have invented that lives throughout the vacuum and doesn't like to be turned off, even classically. It doesn't like to sit here at the zero value because it's unstable. The top of this bump here to fall to a lower energy state, like this. And when it does, it fills the vacuum with a condensate of the quanta of this field, the Higgs field, Higgs condensate, and now the vacuum, even without quantum effects, is full of this field. And the quanta, the particles that are an alternate description of this field. And now when the electron or the quark moves in the vacuum, it continually collides with the Higgs condensate and undergoes a kind of friction, as in a theory of this kind means that it has mass. The quantum vacuum in QCD, in the real world, we believe, doesn't like to have chromodynamic field in it, so it tries to get rid of it, and it squeezes into this tube, and that's what causes the confinement. Now, this is what led to QCD and Nobel Prize, and when you get the Nobel Prize, you get a bunch of things. You have dinner with the Queen and the Crown Princess, a beautiful banquet, and you get a check, which is nice. But you also get a beautiful painting by a Swedish artist, who here you see is depicting three quarks inside the proton, held together by this chromodynamic field. This is what it actually looks like if you do the computer calculation. What happens if you try to pull the three quarks that are inside you? Every proton is a composite made out of 3 quarks. And if you tried to pull the quarks out, the flux, the field, is restricted to this blue region, and again, the energy it would take would be infinite. So this journey towards unification that started 43 years ago, we have no idea where we are in that journey. Something seems to be missing. String theory is not really a theory, it's a framework. We thought it was the answer because, unlike previous theories, it seemed to be a framework, a theory that you couldn't change. You tried to solve the theory and you found there was only one solution. You couldn't vary any parameters, so it was unique. But it turns out there are lots of solutions. Really an infinite number of solutions. String theory, for that reason, is more like quantum field theory, a framework which needs some other input to define a specific theory which is predictive. Perhaps among this enormous class of solutions, one can, by looking long enough, find the correct one. But perhaps something is really missing that picks out the right solution. I actually believe something is missing. We haven't yet come to grips with the real problems facing this unification of gravity, the dynamics of space and time itself, with the other forces and with quantum mechanics.